So now we get to a very important topic. Most of this course focuses on manipulation of arrays. After all, in part 2 we're going to look at vector and matrix operations, and those invariably involve one-dimensional and two-dimensional arrays. So, assignment to array elements is a very important topic for us. So here's the specification. We have an expression E. We want to assign it to the element of B indexed by K. What do we need to do? We need to check if E is a valid expression. If not, then we abort. We need to check if K is in the range of indices of array B. If not, we abort. If we get past that, then we evaluate expression E and assign the result to the element of B indexed by K. In order to do this cleanly, we're going to define something that initially will seem a little cumbersome. So, the expression B with the element indexed by K replaced by the result of evaluating expression E, B semicolon key colon E, is a copy of array B, but with the result of evaluating expression E assigned to the element indexed by K. So here's an example. We have array B, which we will assume is indexed starting with 0, with contents -2, 1, and 3. B semicolon 1 colon 100, B1 100, is then a copy of B, but with the element indexed by 1 replaced by the value 100. So that's this. If we then take that new array and we ask what is in the element indexed by 1, we get back 100. If we ask what is in the element indexed by 2, we get the value 3. Hopefully this makes sense to you. So now we can go ahead and define the weakest precondition. The weakest precondition of assigning the result of expression E to the element of B indexed by K, leaving you in a state where R is true, is given by, well, first of all, we need to check whether the expression is a valid expression. We need to check whether K is in the range of B. And then finally, we look at R and we do a textual substitution of the array B, but with the element indexed by K replaced by the result of expression E, substituted in for every free occurrence of array B. So what we're really doing here is we're looking at the entire array B as one variable, and we are doing an entire substitution of a new array into that. It just happens to be that most of the elements in that new array are just copies of what was already in B. Okay, let's do an example here. What is this example? Well, this is an example that might come from a program that copies the contents of array Y into array X, and we will assume that the first K elements have already been copied, and now we're looking at the entry indexed by K in array Y being copied into the corresponding element of array X. So the precondition says we've already copied the first K elements, and the postcondition says we have copied the first K plus 1 elements. So how do we prove this correct? Well, we can evaluate the weakest precondition. We can instantiate that. We can then do the definition of assignment. So now notice that array X must be replaced by the array X, but with the element indexed by K replaced by YK. We can place that into the occurrence of X. But this is kind of cumbersome because we know that elements 0 through K minus 1 haven't changed. So what we're going to do is we're going to split the range into the part where it has not changed. That's the first part all the way through element K minus 1. And then the separate element indexed by K. If we do that, then in the quantification we can just substitute back in X, because those were all of the elements that were unaffected by the assignment. And then we can substitute in Y of K, because that is the value in X when the element indexed by K is replaced by YK. Then we see that yk equals yk is just true. We can do AND simplification and we get that. And notice that this is exactly the precondition. And since it's exactly the precondition, we know that this code segment is correct because Q implies this. As you know, I like to look at things a little bit differently often. So alternatively, we can ask ourselves what is the weakest precondition and place that where it must be true in our code segment. And notice that we just computed what that weakest precondition was, and then we can ask ourselves the question, does Q imply that weakest precondition? And just by eyeballing this, we see that they are the same, and therefore obviously Q implies the weakest precondition. So this code segment is correct. And let's go one step further. Let's actually reason about what's going on as part of the code segment itself. So here we have our precondition, our postcondition. We've given ourselves some space to doodle and write some intermediate results. And let's see what happens. Well, first of all, we notice that something special happened with the element of x indexed by k. So let's take the postcondition right here, and let's actually separate out the element indexed by k. So we're doing a splitting of the range of the quantifier. What we now notice is that the element indexed by k does not occur in the quantifier, and therefore we can just do a textual substitution of y of k into x of k to come up with the weakest precondition. So then looking at that, we notice that yk equals yk is true. We can do AND simplification, and then finally we can compare what comes out of that with the precondition, and we notice that they are one and the same, and therefore this code segment is correct. So what did we learn from this? We learned from this that actually it's a really good idea to split the range early, because if we can isolate x of k, then the substitution is much simpler. So even when we were just trying to compute what the weakest precondition was, what we could have done is started with this, done the instantiation, then immediately done the splitting of the range to isolate the element of x indexed by k. We could then have done the textual substitution, replacing x of k with y of k, noticing that the quantifier is unaffected. And then we can do algebra. We know that what's in yellow here is true. And simplification. And then we could have inserted that into our code segment at the place where it must be true. And then by comparing the precondition with the weakest precondition, we notice that they are one and the same, and therefore this code segment is correct. The idea of simultaneous assignment extends to assignment to arrays. Here the expressions E0 and E1 should be valid. J and K should be in the range of B, and J should not equal K, because if the two expressions are not one and the same, then there would be some confusion. What is the definition of the weakest precondition for simultaneous assignment to array elements? Well, E0 and E1 must be valid. J should be in the range of B, K should be in the range of B, J should not be equal to K, and then you can do a substitution of a copy of B, but with the elements indexed by J and K replaced by the respective expressions into every free occurrence of B, and there you have the weakest precondition. In summary, this is the weakest precondition when you assign to an element of B. If B is not in the range of any quantifier that involves array B, you can instead simply substitute the expression E for every free occurrence of B of K that occurs in the predicate R. Otherwise, you may want to split the range so that you are in that position. And an example of what I mean by that is, here we have a postcondition where we have isolated the element of x indexed by k. It is that element to which we're going to assign an expression, and that should have been a colon equals because it's becomes. And notice that here we just did a textual substitution of that expression into the occurrence of x of k to come up with the weakest precondition.